This study investigates the degradation of free cyanide and metal-cyanide complexes using photoactivated bismuth vanadate combined with ozone. In this study, we first focus on the characterization of the bismuth vanadate correlates. To begin with, we used X-ray diffraction, and the diffraction pattern revealed that the system crystallizes merely in the monoclinic structure. The morphology corresponded to irregular polyhedral crystals, some of them with a cuboidal shape. The calculated band gap was 2.5 electron volts, which indicate a strong absorption in the UV visible range, while amorphous materials typically show average energies above 150 milli-electron volts. For bismuth vanadate, it was only 88 milli-electron volts, pointing to a high degree of polycrystallinity and therefore a low defeat density. In this case, the particle size distribution showed an average of about 1.35 microns. Its zero potential in the presence of cyanide at alkaline pH was minus 6.2 millivolts, which demonstrates high stability when dispersed in aqueous medium and a strong affinity for free cyanide. Regarding its textural properties, it has been reported that bismuth vanadate generally presents low specific surface areas. In our study, we confirmed this as well, which implies fewer exposed active sites and therefore lower correlated activity. In addition, deviation in stoichiometry may act as recombination centers for charge carriers, further compromising the reaction efficiency. Once the photocorrelate was characterized, we proceed to evaluate its correlated performance, considering first thermodynamic aspects such as the Gibbs-free energy of reaction. For this purpose, predominant zones diagrams were used as a theoretical tool to predict the stability of the chemical expression in solution. As a case study, the aqueous matrix contained trace amount of metallic elements characteristic of post-silver leaching process. Since cyanide is able to form a strong covalent coordination bonds with the target metal cations. Previous diagrams showed that for potential below 0.6 volts versus CHE, metal-cyanide complexes are the thermodynamically stable species across the entire pH range. Specifically, in the case of silver, copper, and iron, the predominant species are those indicated in the diagrams. The experimental results of both free cyanide and total cyanide degradation are shown in Figure 5. The degradation system corresponds to a hybrid process of heterogeneous photocatalytic ozonation employing bismuth vanadate synthesized by the sol-gel method. The degradation of only free cyanide is 100% with a reaction time of 14 minutes. Also, the analysis of the water matrix containing aqueous metallic species and cyanide reveal high efficiency in the degradation of total cyanide. Monitoring the cyanide levels demonstrate that total cyanide degradation was achieved within a 20-minute period. During the first 8 minutes of reaction, a significant degradation percent, close to 80%, was obtained. As the cyanide concentration diminished, the photocatalytic ozonation reaction slowed down due to the reduced ability of cyanide. In figure 5b, UV-based spectra of solution containing free cyanide and metal-cyanide complexes at different reaction times were recorded to explore the evolution of complexes of copper with cyanide. This result suggests that the complex of copper partially dissociate within the first 10 minutes, releasing additional free cyanide ions. As the reaction progresses, these complexes dissociate completely and a broad absorption peak appears around 260 nm, along with a sharp absorption peak at 213 nm, but attributed to aqueous ozone. The stability of bismuth vanadate in the presence of total cyanide was evaluated through consecutive photocatalytic ozonation reaction. As shown in figure 5c, the photocatalytic ozonation activity decreased after the third recycling, indicate the activation of bismuth vanadate. The ammonium concentration determined for both free cyanide and total cyanide after the ozonation and photocatalytic ozonation processes are shown in figure 5d. During the photocatalytic ozonation process, the highest concentration of ammonium was recorded in the system containing only free cyanide, with a value of 86.8 ppm. Meanwhile, the ammonium concentration measured in the total cyanide systems was 22.70 ppm. The thermodynamic analysis after the degradation of total cyanide is shown in figure 6. For silver around pH 11, the predominant forms are silver oxides, a solid phase. Lead behaves differently. Although lead oxide is initially predicted, under oxidation condition it dissolves, and the stable form above pH 10 is a complex species. For the transition of metals, the situation is quite consistent. At pH 10.5, copper is present as copper oxide, iron as iron oxides, and zinc mainly as zinc oxide. In the case of zinc, however, about 10% remains as soluble species in the form of hydroxide complexes. Finally, regarding cyanide, the main degradation byproduct is a cyanide, which predominates at alkaline pH and remains the dominant form in this range. Finally, this study shows that thermodynamic analysis with chemical stability diagrams helped us understand how free and metal complexes cyanide degrade in water with silver, copper, iron, lead, and zinc. We found that photocatalytic ozonation is very effective thanks to the synergy between reactive species, ozone, and the pyrolysis. Ammonium was detected as byproduct and its levels varied depending on the matrix. Bismuth vanadate was stable at first, but after several cycles, its surface became followed with metallic precipitate, which gradually lowered its photocatalytic performance.